Hi, everybody. I'm just going to do these last two questions from the Nearpod that I gave you guys for Tuesday. Oops. Hold on. Okay. So anyway, nope, that's not going to work. So we've got this first question, which is about Risa. She pushes a 10-kilogram chair as shown in the diagram. What's the horizontal net force? What's the vertical net force? How much work does she do? If she lets go of the chair after 1.5 meters, will it stop suddenly or keep going? So let's take a look. First of all, horizontal net force and vertical net force. So you can see this here. Basically what we can see for vertical, we have 100 newtons up in the air and 100 newtons down to the ground. So those cancel each other out. Our vertical net force is going to be 0. And then our horizontal net force, we have 40 to the right, 25 to the left. So our horizontal net force is going to be 15 to the right. Which is a positive 15. So F net horizontal, am I right? H for horizontal is going to be 15 newtons, and you can write it as positive 15. You can just write it as 15, or you can write it as 15 to the right. Any of those would be fine. So if you just put plain 15, that's fine. But I wrote positive 15 newtons to the right. F net vertical equals 0 newtons. That has to be 0 newtons. Next. No. Yep. Oh, well, this is not helpful. What did I ask you guys for next? It doesn't say. All right, next it asks how much work Risa does on the chair. Risa is F push. Right? F push. She's pushing it. So she does 40 newtons. She uses 40 newtons of force across 1.5 meters. Right? So work of Risa is equal to 40 times 1.5 meters, which is 60 newtons. That was kind of an easy one. This question was kind of easy. Oh, well. And then it says, if she stops pushing it, what's going to happen? Is it going to stop suddenly? Or will it keep rolling? Okay. Here's the deal about that. Did Risa start from rest? She started from rest, right? So Risa started from rest. Basically, what's going to happen after those 1.5 meters is that a net force of 15 worked on it for 1.5 meters. So that's 22.5 joules of energy. So that chair will have 22.5 joules of energy after she lets go, after the 1.5 meters. The chair's not going to stop suddenly. It's going to keep rolling. But stopping suddenly to me means that it would just like stop as soon as it left her hands. It won't. So we're going to say it'll stop eventually. So if we say that, let's see, Risa did 60 newtons of work and then, 60 joules, my goodness. And the work done by friction was negative 25 times 1.5. That's equal to negative 37.5 joules. So the total work, W, equals 60 minus 37.5, which is 22.5 joules. So basically what I'm saying, let me get up here. Yeah, get rid of the whole darn thing. Okay, and it doesn't ask you to do this, but I'm just giving you guys a little extra because I know you just want a little bit of extra physics all the time. So if our E1, when she lets go of the chair, it has 22.5 joules of energy plus work, which is force of, the only thing that's going to do work after she lets go is the force of friction times D, is going to be equal to 0 because when it stops, it has 0 joules of energy. We know the force of friction is negative 25 because it says it on the free body diagram. So we can solve for D. We say 22.5 equals 25D. And D is going to be equal to 22.5 divided by 25, which is, I think, 0.9. Yes, 0.9 meters. Again, it didn't ask you for that, but it's saying, hey, is it going to stop suddenly or is it going to keep rolling? It's going to keep rolling. It's going to stop after 0.9 meters. That's a little bit less than 3 feet. So depending on your version of suddenly, either yes or no. But again, it depends on your definition of suddenly. I would say no. I would say suddenly to me means that it would just like stop immediately. Okay, the last, let's see, next one. James and Brian push on a 25 kilogram box as shown. The box initially has a speed of 2.5 meters per second. Find the box's total initial energy, the total work done in the box, and the box's speed after they push it for 4 meters. So box's total initial energy, we have all the information we need. 25 kilogram mass, 2.5 meters per second is the speed. Get that out of there. Okay, I don't want this showing anymore. Why, you guys? All right, so our initial energy is going to be KE1 is equal to 1/2 times 25 times 2.5 squared. And I definitely am going to need a calculator for that one. And we get 78.125. Sure. I am going to go 3 decimal places just because it terminates after the 3rd decimal. All right, then the next part. We need to figure out what is the total work done on the box. Okay. The only 3 forces that do work on this box are Brian, force of Brian, which is a negative 101. Force of friction, negative 85. Force of James. We are not using the 225 version, my friends. We are not using the 145. We are using the 172 because that is the part of his force that is parallel to this positive 4 displacement. So let's go back to the problem. I'm going to erase this. See, that erases a lot better. So the total work done on the box get out of here. No, you guys. Okay, whatever. The total work done on the box is going to be, we've got the force of, let's see, the work of Brian. We'll start with Brian. The work of Brian is equal to the force of Brian, which is negative 101, times the displacement, which is 4. So he has a negative 404 joules of work. The work done by friction, which is negative 85 times 4, which I want to say gives me, if I had to guess, I'm not going to guess. I'm just going to calculate it. Why not? Oh, it gives me negative 240, probably. 85 times 4, 340, negative 340 joules. The work of James is that 172 times 4. This gives me 688. I know this because I just did this question last period. It's not that I know that in my head. I'm going to add those all together for total work. For total work, I'm going to get, when I do that, 688 minus 340 minus 404. I get negative 56 joules. This is my total work. So W, you can call it WT, whatever. W total, negative 56 joules. The last one, I'm going to erase this, so pause it if you need it. The last one asks us to find how fast is it going to be going after those 4 meters? Well, during those 4 meters, that box lost 56 joules of energy. So we started off with E1 of 78.125. I'm pretty sure. I think I lost that, so if that's wrong, whatever number I had before is good. Okay, the W that we just calculated was 56. That's going to be equal to E2, which is KE2. This box is on the ground. It's not going up. It's not going down. It's not getting any GPE. So I'm going to say that 22.125 is equal to 1/2 times the mass of 25 times V squared. And again, I'm really hoping that my numbers are correct. I'm remembering them. Actually, I can check. Yeah, 78.125 and 56. Great. All right, and I just checked that I added that correct or subtracted that correctly. All right, so I get that v squared is equal to 1.77, which means that v is equal to 1.33. Does this make sense? Well, it should, because I had an initial speed of 25 or 2.5 meters per second, so I definitely am getting slower. 1.33. Sure, we'll go with that. That makes sense.